Hello everybody and welcome to this video, which is all about the stages that all stars go through in their life cycle, including the star that we all know and love and affects our daily lives, the Sun. You can see on the screen a simplified diagram that represents the stages that all stars go through in their life cycle. Depending on how big or small that star is, will determine which stages it goes through in the later portions of its life. As you can see here, after a star becomes a red giant, it splits into multiple options depending on how big or small that star is. Before we talk about this entire life cycle, let's talk about the purpose of this video. By the end of this video, you will understand all of the stages that stars go through in their life cycle, and you'll be able to apply that knowledge to tell the story of our sun, a star in itself. You'll be able to tell us, how was the sun born? What is the sun doing right now? How will the star age? And how will our sun, aka the star in this story, how will it die one day? And how will that matter cycle back through the life cycle again in another star? You'll be able to demonstrate this knowledge in a number of different ways, and that will be your last summative of this semester. So as we're going through this, keep in mind the summative and the end goal, and think about when we talk about each stage of the star life cycle, think about how that would look with our sun and how that would affect humans on Earth. The first thing we need to talk about in the star life cycle is gravity. Everything with mass has gravity. This is a very difficult concept for us humans on Earth because there is only one thing that we feel like has gravity because it is the dominant source of gravity, and that's the Earth, right? Everything is pulled down to the Earth. Gravity is holding this cup down on the desk, my butt in this seat, our car to the ground when we're driving. But the truth is, anything with mass has gravity. So this cup, for example, actually has its own gravitational pull between the mass in my body and the cup, but I don't feel it because that mass from the Earth pulling down on my body is so much stronger than the mass that this cup is pulling with. The more mass something has, the more gravitational pull it's going to have. That's why the Earth has such a strong gravitational pull, and we don't feel the attraction of anything else. But if we were in space and away from a bunch of large objects, this cup, if it's just floating around in space and I'm also floating nearby, these two objects are just going to naturally come together and be attracted to each other because that's gravity. Any two objects with mass are pulling towards each other. So on Earth, we don't experience that attraction because we're always pulled to the Earth. That is the dominant source of gravity for us. But that has a big effect on stars when they're forming in the early stages of their lives, which we will talk about right now, the very beginnings of the life of a star. And when I say beginning, it's not really the beginning, because stars are constantly, the matter that makes up stars, the stuff in stars, is constantly cycling through this first stage, to the middle stages, to its death as a star, and that stuff left over cycles back into a new star. So we're going to call it the beginning, but know that this is actually a continuous cycle. We just got to start somewhere when we talk about it. And we're going to start by talking about stellar nebulae. Now that's the plural for a nebula. A nebula, you can think about it like this. It's a cloud of gas. Mainly hydrogen and helium make up these nebulae. These are called stellar nurseries because these clouds, this is where stars are born. So when that force of gravity, remember, anything with mass, anything with some sort of matter in it is attracted to other things with mass through gravity. If there is no other dominant force of gravity in that area, those two things that we think of as very light will become attracted to each other. That happens in these clouds of hydrogen and helium, in the nebulae. Those particles slowly start coming together And it's a chain reaction. The more that start coming together, like first we have 2 that come together, and then 4, like a few more join. Eventually, that's starting to get kind of big, right? The bigger it gets, the more mass it has, and thus more gravity. Because remember, things with more mass have a larger force of gravity. Just like the Earth is huge, right? That's why it has such a strong force of gravity compared to other things we know. So as these things are starting to come together, due to that force of gravity itself becomes stronger and attracts more things. And then the gravity gets stronger because it's getting bigger, and it's a cycle. It builds on itself. Eventually, that's going to get to a point where it gets so dense and big that we call it a star. But not yet. It's still a nebula. Now, this condensation, this clumping, this coming together to form a star, this could also happen if there was a shock wave moving through this nebula from a supernova. We'll talk about a supernova later. So when that stuff comes together, at a certain point we're going to call it a star, but not yet, because something key needs to happen, and that's nuclear fusion. Nuclear fusion is what makes something a star. It is not happening yet. We only have a nebula, which remember is a cloud of gas, hydrogen and helium mainly. We have a picture of a nebula right here, and a few more. On the left, we have the Eagle Nebula. So look at this. It's actually just a cloud of gas and dust. Hydrogen and helium. Here we have the Crab Nebula. It's a cloud of hydrogen and helium. It looks quite beautiful, right? The gases, when they're ionized in space, they give off these nice colors. So it looks cool, but these are stellar nurseries. Eventually, these gas particles, due to the force of gravity between them, will start to come together, clump together, and it'll get to a point where it is so dense that nuclear fusion occurs, and we call it a star. But not yet. When it starts to act like a star, but it is not a star yet, we call it a protostar. A protostar is like a baby star. Aww, cute little baby star. Protostars look like stars. They start to glow. They start to get warm because we're getting so massive. We're getting so many gas particles together. And that extra force, because the gravity is so strong, is starting to create some heat and light that we see in these pictures. But it is not creating its own energy yet. That is just the force of gravity so far. There is no nuclear fusion. When we have nuclear fusion, we have a star. But we're not there yet. We only have this baby star, a protostar. So, in between stellar nebula and a real star, we have this protostar, which is like almost a star, but not yet because no nuclear fusion. When that nuclear fusion occurs, we have a star. A star is born. When an average star gets massive enough that the force pulling in on itself, that gravity, is strong enough to create nuclear fusion, which we'll talk about what that is in 1 second, that's when we call it a star. This process of nuclear fusion creates a ton of energy. And this is why our sun, the star we all know, it feels so hot to us and it's so bright. Because in the core of this star, the sun, nuclear fusion is occurring. And it's giving off a lot of energy. So this nuclear fusion is caused by the pressure of that gravity pulling in on itself. That gravity is so strong that those things in the center are just getting squished and forced together in fusion, which is where the word fusion comes from. They fuse together. Nuclear fusion is when 2 smaller elements literally fuse together into one. Just like you see in this diagram down here. 2 hydrogen atoms in the core of a star, when that gravity is so strong, and it has to be really strong to force 2 atoms together. When it is that strong to overcome the force of repulsion that atoms normally have with each other, they fuse. And what we get out of that is a new atom, a bigger atom that contains all the parts of those 2 original atoms, and some leftover energy, maybe a leftover neutron or another leftover particle if there were a lot. That energy is what we feel as heat and what we experience as light on Earth. As stars get older and older, they get bigger and bigger. They get heavier and heavier. That gravity continues to cause nuclear fusion to occur. And even those bigger elements that are made as a part of fusion, they also get fused into even bigger elements. So this is how elements are created as well, actually. As you can see here, helium and helium can get squeezed together in this process of nuclear fusion to create another bigger one, beryllium in this case. If there happens to be a beryllium and a helium in the core of the star, they get squeezed together. That could make carbon. Down here you can also see how carbon and helium getting squeezed together in the core of a star due to that tremendous force of gravity can create oxygen. This not only creates elements, but also it creates that leftover energy that we're talking about. So to go back, this is how elements are created. The oxygen that we breathe, the carbon in my skin cells, those were all made in stars. Stars are like element-producing factories. They can make only light elements, though. Anything with an atomic number of 26 or less, which on the periodic table is iron. The reason for this, a little complicated, but in simple terms, when you get to a star core that has iron in it, that core is going to become unstable. And that will cause a star to become a supernova, which is a huge explosion. So we cannot have elements heavier than that in the core of a star, or it becomes unstable. So stars, through this process of nuclear fusion, they create light elements like oxygen, carbon, helium, anything with an atomic number of 26 or less on the periodic table. Hydrogen, helium, beryllium, those small elements that go into the nuclear fusion reaction, you can think about that as like the gas in a car. This is what makes the star run. This nuclear fusion is what makes it a star. Just like if you don't got gas in your gas tank in your car is not going to function properly. If there's no light elements to go into a nuclear fusion reaction, or there's not enough force for that nuclear fusion to occur, for those atoms to get squeezed together, that star is not going to function properly. And it might turn into a different type of star. So in normal stars, like our sun, what's happening is our gas is these small hydrogen atoms. Different isotopes of hydrogen have these names: deuterium, tritium. If it has just one plus, it's a hydrogen. The gist of it is, when two light elements are going into a reaction to produce helium and energy, that's what's going on in our sun right now. We call that an average star, or a main sequence star. So, we just talked about how stars in a nebula form through the stage of becoming a protostar, and that gravity condenses it enough where nuclear fusion occurs and it becomes an average star or a main sequence star. Let's talk about how a star becomes a red giant, like our sun will one day. Our sun will, right now our sun is right here, it will become a red giant one day. And that will happen when it runs out of that fuel in its gas tank. When there's no more hydrogen in the core of the sun for that nuclear fusion reaction to occur, that star, the sun, will become a red giant. When a red giant is formed, basically what's happening is we're changing from a nuclear fusion reaction where two hydrogens turn into helium. We're changing now to a new nuclear fusion reaction where two helium will form either beryllium, or beryllium and helium will form oxygen or carbon. We're fusing heavier, but still light elements because they're under atomic number 26, but heavier elements this time. So when a star becomes a red giant, we know that it is no longer fusing hydrogen into helium. It is now fusing helium into heavier elements. So that's what makes a star a red giant. And that change in nuclear fusion reactions messes with the amount of force going out from the core because of the reaction and the amount of gravity coming in. So because there's so much more force coming out from the core now, that star is going to get huge. And because of the physics of it all, the star changes color. It becomes red. But that star becomes bigger because all of a sudden we have way more force pushing out from the core. It's a red giant. So that only happens when we run out of fuel in our gas tank and we got to start using a different type of fuel. We've ran out of hydrogen and now we got to start fusing helium if we have enough force of gravity to force two helium together. Because the larger the atom is going into the nuclear fusion reaction, the more force you need to put them together. So someday our star will become a red giant, but not for several billion years because we got plenty of hydrogen in the core for that nuclear fusion reaction to occur. Here's a nice comparison of the size difference. So you have to picture in this little guy over here, which, I mean, not actually small, right? When you look in the sky, you can see that the sun is actually pretty big, considering how far it is. But compared to a red giant, it looks tiny. You have to picture that nuclear fusion reaction that's occurring in the sun versus this red giant is not nearly as powerful. When you're fusing hydrogen into helium, like we are in the sun, it's not nearly as powerful as when you fuse helium into beryllium or carbon or oxygen or silicon. So when that reaction occurs, helium nuclear fusion reaction, there's way more force coming out from the core, and that kind of pushes the boundaries of the star way out, which is why it gets so big and so much brighter in the sky. So this will definitely affect humans on Earth, but not in our lifetime, of course. But if our planet survives 5 billion years down the road, that change from a normal mainstream star to a red giant is going to change the habitable zone of our solar system, meaning where is the temperature in our solar system good for life? Where can life survive in our solar system? Right now you can see the Goldilocks zone, as it's sometimes called, is right around Earth and Mars. But as this star becomes a red giant, that will push out to Jupiter and Saturn, being planets where the temperature is just right for life. So it will definitely impact humans that way, if we make it that far. A funny thing happens also, which makes total sense in the core of a star. As it turns into a red giant and starts to fuse these heavier elements, based on how dense, how heavy those atoms are, we start to get layers in the sun based on that density. As you can see in this diagram here, in the very center we have the heaviest element that can be made in nuclear fusion in a star, which is iron. Out from that we have the next heaviest, but a little lighter than iron, silicon, then magnesium, neon. It's a gradient from the heaviest elements that can be made to the lightest. And in each of these zones, a different nuclear fusion reaction is occurring. For example, in this orange zone, you can see hydrogen fusion, meaning hydrogen are coming together to form something heavier. In the next one, you can see helium is what's coming together. And carbon, the next one, etc. Because the deeper in you get, you have to think of yourself in the core of a star. The deeper you get into the core, the more stuff you got over you. Just like the deeper you get in a swimming pool, the heavier that water feels, like maybe your ears start to pop. That's why it's really hard to go deep diving, because the more you got over you, the more gravity pulling down on you, the stronger that force feels. Just like in a star. So we start to get layers as well in these red giants. Okay, so we just talked about how a star becomes a red giant. Now we're going to talk about how stars die. And that depends on how big the star is. How much mass does it have? There are two routes we can go. If a star is really massive, huge stars become supernova, which eventually becomes a black hole before that matter cycles back to a nebula. If a star is not that big, like normal-sized star, like our sun, that's going to become a planetary nebula. Eventually, that leftover core will be called a white dwarf. So normal-sized go this way through planetary nebula, and large stars become a supernova. Let's talk about the planetary nebula first, as that's how our sun will die. During this stage, again, it all depends on how much gas do you have in your fuel tank. Do you have the ingredients for nuclear fusion? When stars run out of what they need for that nuclear fusion reaction to occur, the star does this thing where it puffs out its outer layers, its outer atmosphere, in what we call a planetary nebula, and leaves behind its hot core. Just like you can see in this picture of a planetary nebula, only the core of that star remains, and the rest of that is lost. It's puffed out. It's just floats into space, and that stuff becomes a new nebula where new stars are formed. As you can see, the core, the super hot core, is actually really small compared to our sun. It's about the size of an Earth. So very small core is left over, extremely hot. We call it a white dwarf. And that white dwarf will just cool off over millions of years and eventually become a brown dwarf and sort of like harden like a rock. So that's one way that a star can die. If it's a huge, supermassive star, this star will die as a supernova. It will end its life cycle in a huge explosion. And supernovae, the plural, are pretty important because this is how we get elements with an atomic number above 26. In fact, the only way that elements with an atomic mass above 26 can be formed is through a supernova. So that includes all of the metals that we have on Earth, in your smartphone, in your watch, in your car. Well, some of those metals, like aluminum, are under atomic number 26. But things like uranium, plutonium, titanium, all of these things, mercury, were all made in a supernova. And it's the only way that they can be formed. So for metals like uranium to be on Earth right now, they must have gone through the life cycle of a supermassive huge star, died, and all that stuff is just shot out into the universe in every direction. Some of that stuff starts to clump together because of this force of gravity, and it ends up on asteroids, and it makes its way to planets and solar systems in that way. Some of that stuff is just floating around out there, and it starts to clump together because of gravity, and it forms a planet like Earth. So the metals on our planet, like uranium, plutonium, those heavy metals, they were all formed in a star explosion, supernova. So not only are the light elements from the periodic table made in a star through nuclear fusion, but the heavy elements are also made in stars through these supernovae. So really, everything in the universe, besides hydrogen and helium, which is left over from the Big Bang, all of that stuff was made in stars. We are made of stardust. Not joking. Everything, all of those elements are made in stars, whether it's nuclear fusion or a supernova. All right, so we have always struggled to see what a black hole really looks like, because the force of gravity in that black hole, which is left over, it's the core of a supernova star. When that star explodes, it leaves behind its core, which it collapses on itself and becomes a black hole. A black hole is called a black hole because its gravity is so strong that not even light can escape. So even light is sucked into this source of gravity. It is that strong. Here's the first ever image taken by a scientist from NASA of a black hole in 2019, so pretty recently. This is an image from Katie Bauman. At the end of that life cycle, whether our star has become a white dwarf and puffed out its outer atmospheres, or a supernova, its core has collapsed in on itself and become a black hole, that matter starts to cycle back. It becomes a cloud of gas floating around in the universe, which starts to clump up, group up because of the force of gravity between the objects, and starts to form new stars. It's a cycle. And we just completed one full round of that cycle. So, this was a simple overview of the life cycle that stars go throughout their lives, which could last a few billion years or 15 billion years, or even longer. So if you'd like to read further details and learn more about the details of more complicated diagrams of star life cycles, you can check these out. And also, there's a few articles linked here that you can read about that will tell you all the details of the stages that a star goes through in its life.